Okay, so here's the approach you need to take. This is a really good review for the test. And I'll just show you kind of how I think about a problem like this. When they ask me to find when something is concave up, right, I'm thinking, well, what do I need to know? I need to know when the second derivative is greater than 0. And then when they ask me to find if it's concave down, I need to know when the second derivative is less than 0. Or when is the second derivative positive? When is the second derivative negative? That's my justification right there in orange. That's all I need to do to justify, right? Is indicate it's concave up because of this and it's concave down because of this. Well, what that means then is I have to actually do that work. Right? I got to find the derivative. Well, notice this is a product rule. And you do not have to show the work for this. But we know that the derivative of the first is 1. The derivative of the second is e to the x. It's itself. So if I do the product rule, it's the derivative of the first times the original second. So 1 times e to the x plus the first times the derivative of the second, which is x times e to the x. Now I don't have to figure out anything with that first derivative because concave up and concave down is really just based off of the second derivative. So I have to take the derivative again of this function. Now notice 1 times e to the x, that's just e to the x. I really don't need that 1 here. So the derivative of e to the x is itself plus, now here's something you can notice. You're going to take the derivative of this product. So you got to do the product rule again, but wait a minute. Isn't that what we already did? So we have the work set up here. I'm going to use just that same format. The derivative of the first times the second plus the first times the derivative of the second. However you make a connection to that, but here's my second derivative. Now, it can be simplified. I have e to the x plus e to the x. That's 2e to the x plus, now I can't add the x e to the x because that's a different constant. So, but now I need to set the second derivative equal to 0. And when I do that, I'm actually going to factor out something they have in common. It's too many lines. That's confusing. They each have an e to the x here, so I'm going to pull an e to the x away. I factored out an e to the x, and now I'll use the zero product property. Each individual factor is equal to 0. Now here's something you might remember. The natural log graph, or excuse me, e to the x graph is exponential. It will never equal 0. If you don't remember that, then we have to take the natural log of both sides, and I get the natural log of e is just x, and the natural log of 0 does not exist. So I didn't need to officially solve all that because I know my answer is not going to come from this part right here. But then if I bring the 2 over, I get 1 point that is a potential inflection point. All right, so what did I do? I took the second derivative, I factored it, and set it equal to 0. Now I'm going to basically confirm what type of sign change is happening in the second derivative at my potential point of inflection. Right? So I need to now look at this derivative, the second derivative. You could look at any form of it. I like the factored form. And here's the reason why. There are some tricks you can use to help yourself when testing values. Right? I need to test a point to the left of -2. Let's test -3. Now, if I put a -3 right in here for x, e to any power will always be positive. This e to the x is always going to be a positive value, so I don't really have to worry about the sign of this part. It's the second factor that basically controls the sign, and if I plug -3 in, -3 plus 2 is -1, and a negative times a positive tells me it's a negative second derivative to the left of 2. All right, and now let's test another point. Let's test 0. That is to the right of 2. So if I plug in 0 here, e to the 0 is 1. That's positive. 0 plus 2 is positive. So a positive times a positive gives me positive. Okay? Now, this sign chart is not enough work for the justification, but we do know all our answers. I should state what is concave down. If I just said it is concave down, that's not good enough. We want to be specific. What is it? It is the function y. So y is concave down, up. Let's deal with concave up first. Y is concave up on the interval from -2 to infinity. That's where we have a positive second derivative. So my justification is real quick, because y double prime is greater than 0. That's all you need to write for your justification. Okay, so there's my first answer. Y is concave down on the interval from -infinity to -2. And the reason why is because y double prime is less than 0. Right? Okay. Now, the nice thing is right here at x equals 2, we have a change in signs. So we're almost done with this point. We know there's an inflection point at x equals -2, right? And the reason why is because the derivative, the second derivative, changes signs. That's your justification. There's only one thing that's missing in this explanation. And they said find the inflection point. A point is xy. They're most likely not going to give you this xy. When you see the point, you need to find both the x and the y. Well, we know what x is, right? We have to find y. And when they're talking about points, you always go back to the original problem. And I'm just going to plug in -2. So what is y of -2? When I plug -2 in, it's -2 e to the -2. Now, I would leave it like that, but if it was a multiple choice question, they would take e to the -2 and bring it to the denominator and make it a positive exponent. So this is probably how they would write their y value. So we're going to continue our work from last week, Friday, and we're going to look at sections 5.3 and 5.4. And we are still basically looking at this idea of what do we know about the graph of f? So what do I know about the original graph if I'm giving information about f prime and f double prime? So we're going to go through a lot of theory on this, and you might not want to write down everything. But hopefully this will kind of help paint a better picture for you of what we're doing. So the big idea here is, how can I take what I know about the derivative or the second derivative and make conclusions about the original graph? Okay. I don't think you need to write this one down. We're going to do this really quick, so don't write this slide down. I just want you to think of, well, what if I had the original graph? We're going to actually relate this to motion. So the graph shows the position function of a particle moving along a line. So remember, position is just kind of like your original function f of x, but instead of using f of x, we usually use s of t, or sometimes we call it x of t. It's just your position function. So it tells you your location. So then here it says, when does the particle's velocity equal 0? What connection do we need to make? Well, velocity is the derivative of the original function. So if I have the original function's graph, and I want to figure out when is the particle's velocity equal to 0, another way I could say this is, when is the particle stopped? Right? So if I have a 0 velocity, that means I'm at rest or I'm stopped. Well, how do I know when this function is at rest? It's at rest when it has derivatives equal to 0. So anytime I have a max or a min on the original graph, then that point has a slope that is 0. Its tangent line is 0, which means its velocity is 0. So how would I answer this? The question is when. We would say this is about 2.8, 6, and maybe 9.2. Actually, I should be careful because these aren't x's. They tell us that they are t's. Okay, but what about, when is the particle's acceleration equal to 0? So now we got to think about, well, wait a minute. If acceleration, if velocity is the first derivative, then acceleration is the second derivative. And I want to figure out, when does the function have 0 second derivatives? Well, that's the part where we got to find the inflection points. Okay, so this ties into the warm-up we just did a little bit. Let's look at this. What do I know about this function from about here to here? Well, it's concave down. Right? This is opening downward, and it's opening downward from here to here. So I know the second derivative has to be negative on these 2 points, or I could say that the acceleration is negative. The acceleration is negative when the function is concave down. And then we know that when the function is concave up, the acceleration is positive. So what about the spots at which the acceleration is equal to 0? Well, those are the spots where the concavity changes from concave down to concave up. And there are 2 locations where those spots are changing concavity, right? Right here at 4.5, there's changing from concave down to concave up, and then right here at about 7.5. Okay. Now, really quick, I kind of want to just put a little note here. What does this green line tell me? What does the blue line tell me? And we already know what the purple dot is, right? That's your point of inflection. So let's see. What do I know about the green part? Well, the original function is concave down. And if that's true, what does that tell us then? It tells us that the second derivative has to be negative, because that part of the graph is concave down. So I know that the acceleration, which is the second derivative, would be negative. And then what about the blue part? The blue part is where the function is concave up. So I know that this part is opening upward, which means the second derivative has to be greater than 0. Okay? So this is just a little bit of an idea of how it ties into motion. But we're going to be analyzing graphs today. Now, this is basically the same thing. If you could do a really quick sketch here of a parabola, and we want, let's say that this maximum is at the point 0.25, I don't know, 7. And then let's say that this point is at 3, 0. Okay? Very first thing you do before you even approach a problem like this is you have to know what graph are you looking at. Because we can give you the original function, the derivative, or the second derivative. And that's the part here. They either tell you in the directions or somewhere in the problem, or the graph states that. Usually it's written more than once. But this is the function of f of x. So it's your original function. You can think of it kind of like your position function, right? That tells you the distance traveled. So my goal is to analyze this graph and figure out where are the critical points, inflection points, concave up and concave down. We basically just did this on the last slide. So I'm going to pause for a moment, and I want you to answer A, B, C, and D based off of the original. All right, let's go over this here. I ended up adding a couple of things just to help us do this. So if I tell you to find critical points of f, critical points are where the derivative, the first derivative is equal to 0 or doesn't exist. Well, where is the first derivative? That is where we have horizontal tangents, and those occur at maxes and mins of the original function. So we know that the x value is 0.25, and the other x value where it occurs, the minimum, is at x equals 3. So I have critical points here. And I do know that those change signs, because look at the slopes leading up to that point. Here the slopes go from positive to negative, which is why this is a maximum. And then the slopes go from negative to positive, which is why this is a minimum. Okay? Now, where do the inflection points occur? Well, the inflection points occur between concavities. So I have to look at my graph, and I got to think about where does this function go from concave down. So notice the green part is concave down, and then it goes from concave up. So if this was a test question, it would be a little more specific, but where does the points usually occur? It occurs in the middle of the max and the min, which we're not going to be perfect here, so any answer that you gave that was close to 1 point, I don't know, let's see. Oh, by the way, sorry, this should be a negative 0.25. I almost made that mistake because it's on the left-hand side of the x value. Oh, thank you, guitar. I just saw that. Yep, so that's negative. And then halfway between that would be, I don't know, let's just say 0.4. Up 1, 2, 3, 4. And this isn't perfect. I'm just making these up. So, but the inflection point would occur at 1.4. Now, this says plural. There doesn't always have to be, sometimes there isn't any, right? If a function is always in a concave up or always concave down, it's not always guaranteed to be there. So here's my inflection point. If they wanted the x and y values, we could put the x and the y values there. I'm just going to put the x's here. Well, then find the intervals where f is concave up. That's the blue portion of the graph. So from 1.4 all the way to infinity. And then where is the function concave down? That's the green part of the graph from negative infinity to 1.4. So when you're given the graph of the original function, these values are pretty quick and kind of easy to find, right? It's easy to see what's concave down and concave up. Where the challenge comes is what happens now if I give you the graph of the derivative? How do we find the same values based off of this information? Okay. So I'm going to change one thing about this problem. We're actually going to look at the exact same graph, but instead of calling it the graph of f, we're going to call it the graph of f prime. So notice, now I just relabeled the graph. It's still the exact same thing. And don't get confused by that. We're just so we still know those points are true if we need them. We don't have to use all of these. Okay, but that's the given information. But now this is the graph. I would write this one. I would definitely write this one. Okay, so think of this graph as like our velocity function. The questions haven't changed. Find the critical points, find the inflection points, find the intervals where f is concave up and concave down. And we're going to do this one together here. Look at the way we think about this. All right, critical points. Well, what has to be true? Before I even look at the graph, I'm thinking critical points. Well, what has to be true? Where does the derivative equal 0 or doesn't exist? Okay. Well, now wait a minute. Where does the derivative equal 0? This is the graph of the derivative, so I'm looking for the spots where its output is equal to 0. That's the two spots right here. So now this function has a critical point. Let's call this -2, 0. So we got one critical point occurring at -2, and the other one is occurring at x equals 3. And the reason why is because the derivative is equal to 0, and this is the graph of the derivative. I'm going to actually add two more things from this. My eraser works. There we go. So from this point, if we know the critical points, let's look at where f is increasing. There we go. Well, f is increasing whenever f prime of x is greater than 0. Well, okay, this is the graph of f prime. It is increasing whenever we are above the x-axis. And by the way, if you really wanted to, let's make a sign chart. Making a sign chart from a graph could help answer a lot of questions very quickly for you. Let's look at what we just discovered. The slope is equal to 0, or f prime is 0 at -2 and 3. Now let's look at the sign value to the points to the left of -2. Okay? So notice, to the left of 2, all my values are below the x-axis, which means the derivative is negative. What do you notice about the spots between -2 and 3? All of the values are above the x-axis, so the slopes will be positive. And then after 3, we actually have positive values as well. So this information, some students like to put negative, positive, positive, positive as just looking at values on here instead of doing the sign chart. But now we can answer the same questions. When is f increasing? Well, it's increasing whenever you have a positive slope. And I got a positive slope from -2 all the way to infinity. Okay. You could also write this as -2 to 3 and 3 to infinity. I've seen it written both ways. Officially, this is a 0 slope. They accept all of this, this answer or this one, because it's basically showing that it's still positive. Okay, well, likewise, where is the original function decreasing? Well, it's decreasing anytime the derivative is negative. And we know that is from negative infinity to -2. So the first derivative can tell us a lot of information just about the original function. And actually, notice here, we go from decreasing to increasing. The original function has negative slopes to positive slopes. That means there's a minimum that's going to occur at this critical point. And then I go from positive to positive. That means we're not a max or a min. Since there's no sign change, there's a flat spot here. Okay. So we know that there's a minimum, we know there's a flat spot, we know where the function is increasing, and we know where there's critical points, all from the first derivative. All right, so hopefully that's somewhat comfortable. Here's where it gets a little tricky. The next 3 questions. How do I know where we have inflection points, where there's a change in concavity? How do I know where a function is concave up? And how do I know where a function is concave down? And how do we know this? Looking at the graph of the first derivative. Okay, so let's think of what we know. This is the way my brain works. I know that inflection points occur when f double prime is equal to 0 or it does not exist. And since this is a smooth, continuous curve without any corners, cusps, or vertical tangents, we don't have to worry about the does not exist. So I'm looking for when does the second derivative equal 0? Well, wait a minute. This is the graph of the first derivative. So I'm really looking for when does the first derivative have slopes that are 0, because I'm just one derivative away. So if you have the graph of the first derivative and you're looking for information about the second derivative, you're checking the slopes of f prime. So what are the slopes of this graph, or when are those slopes equal to 0? They're equal to 0 whenever I have a max or a min. So we have an inflection point at negative 0.25 and x equals 3. And the reason why is because our second derivative is 0, or the slope of f prime has horizontal tangents there. Okay, so these next two are kind of based off of that same logic. Here's the way I kind of think of this. Is what do we know about the second derivative if we're concave up? We know that the second derivative must be greater than 0. Well, what does that imply? That implies that the first derivative, I'm checking, remember, when I'm checking the second derivative and I have the first derivative, I'm checking the slopes of this line. So what I'm really checking for is, when is f prime increasing? Right? When are the derivatives? If I was to check the tangent lines, notice the slopes. The slopes starting on the far left going up to this maximum, all those slopes are positive. And then if I go from the minimum to the right, all of those slopes are positive. So that's where f prime is increasing, or f prime has positive slopes. All right, so my answer here is our original function, f will be concave up from negative infinity, positive slopes, and then from 3, so negative infinity to negative 2.5, and then I have positive slopes again past 3. So from 3 to infinity. All right, last piece for this derivative is, when is the original function concave down? All right, well, I'm thinking about it. Concave down is when the second derivative is negative. But we're looking at the first derivative graph, so the only way to get a negative second derivative is if the slopes of the first derivative are decreasing. So where do I have negative tangent lines? Between the max and the min. My original derivative is decreasing. My answer is f will be concave down between negative 2.5 and 3. That's about as hard as it gets right there. And most of the AP tests will give you the graph of f prime, because you can see all the stuff you have to think about just to figure that out. So now I have the graph of the second derivative. If you want to, you could think of this as the acceleration function. So let's look at what we know from this information about the original point, or the original graph of f. And we're going to try to answer the same questions So draw a rough sketch just to make sure we're all on the same track. Let's call this -2. This will be -6. And this has one of those weird flat spots at -3. Okay, those are the important points. We don't need to really know the rest of the values. And I would write this one as well. And I'm going to start with right here. Critical points are where the derivative is equal to 0 or it doesn't exist. Well, we have a problem here. We are one derivative past the derivative, and to go backwards and look for when the derivative is equal to 0, right now this is not possible. So if you're given the graph of f prime, you can only conclude, or excuse me, if you're given the graph of f double prime, you can only conclude things about the second derivative. We can't go backwards to find derivatives. We might be able to conclude something about the third derivative, which would be considered jerk instead of acceleration. But we don't go that far. We're stopping here at the graph of the second derivative. So let's look at what we want to focus on then. Inflection points. All right, what do we know? Well, inflection points occur when f of x is 0 or it does not exist, plus there has to be a sign change. Okay. Now, once you get good at this, you'll be able to look at this graph and be able to quickly figure out where there are points of inflection or not. But here's my recommendation. You have a graph, and this graph can also be written as a sign chart. And now notice how I labeled this. This is f double prime. And I'm looking for the possible points of inflection. Right? That's -6, -2, and 3. Those are the spots where the second derivative is equal to 0. And there aren't any corners, cusps, or vertical tangents, so we don't have to worry about the does not exist part. But then, for it to be a point of inflection, we have to have a sign change. It has to go from concave up to concave down, or concave down to concave up. So now we're going to read and notice anything below this line, f double prime of x is negative. And then anything above that line tells me the second derivative is positive. So let's make a sign chart based off of this knowledge. All right. Well, to the left of -6, my values are below the x-axis, so that's negative. To the right of -6, all the way to 2, so the spots in between -6 and 2, those are above the x-axis. So that means the second derivative is positive, because again, this is the graph of the second derivative. And then the points between -2 and 3 are all below the x-axis. So that's negative. And then any spot past 3 has a positive second derivative. So notice my sign chart for the second derivative confirms that there's sign changes plus the sign change at -6. At 2, we change from positive to negative, and at 3, we change from negative to positive. So I can now say that the original graph of x of f has points of inflection at those three locations. If I ask you to justify this, here's your justification. It's the orange piece. All right. Well, look how easy or fast the next two questions are going to be because of the way we looked at the sign chart or because of how we labeled this. Find the intervals where f is concave up. So when is the original graph concave up? We know that's true when the second derivative is greater than 0. So you have that information right here. All the pieces that are above the x-axis would be considered concave up. Actually, I don't want to write that there. But let's look at, you also have it on your sign chart. So the intervals that you're concave up are from -6 to -2. And you can put the union symbol, that's how Delta Math does it, from 3 to infinity. All right, and the last one, where is the original function concave down? Well, it's concave down anytime the second derivative is negative, so that would be anything below the x-axis in the graph of the second derivative, or you can just read your sign chart. From -infinity all the way up to -6, combined with -2 to 3. Here's what you know. If you're given the graph of the second derivative, what can we conclude? Well, we can conclude if it's concave up, because the second derivative is positive. We can conclude if it's concave down, because the second derivative is negative. And if it's a linear line, you can see that pretty quickly. Here's where it becomes the original function is concave up, because it's positive, the original function is concave down. We also can conclude that there's a sign change in the second derivative right here. So what if this graph was 6x, right? That's just a linear equation. What would we know about the original function if we were given the second derivative? Now these are going to be connected. So I took someone's derivative and I got 6x. So we can conclude all these things. We could conclude when the original function is increasing or decreasing based off of the first derivative. But notice in this specific problem, the function is never decreasing because the original function is never decreasing because f prime of x is never negative. Notice how it doesn't drop below. That means my function is always going to be increasing. Okay, that tells us something about the original graph. And then we know there's a critical point at 0, but there isn't a sign change, so that it's not going to be a max or a min. The original spot would be a flat spot. And then we also know, because the derivative is decreasing from the left to the right, it's going to be concave down on that interval, and then it's concave up to the right of 0 because f prime of x is increasing. And then we change from decreasing slopes to increasing slopes, so we have the point of inflection as well. So here's what I want you to think of. If you're given f double prime, you can conclude concavity up or down and points of inflection. If you're given f prime of x, you can conclude when the original function is increasing or decreasing, when there's critical points, when there's concave up, concave down, and inflection points. So you basically can conclude almost everything from the original graph of f prime. Okay, and this graph is a parabola opening upward. It could be the graph 3x squared, because notice, 3x squared, the derivative of 3x squared is 6x. So if I work backwards, I could find the graph of the original function. Well, what about whose derivative might have given me 3x squared? Okay, and again, you don't have to write this, but what would the function f of x be if whose derivative gave me 3x squared? Well, x to the third. Right? If I take the derivative of x to the third, I get 3x squared. So look at what this graph does. It hits all those things that we kind of just talked about. You can see the spot where we're concave down and concave up, which was the same interval that we talked about here. So anyways, I will post this slide because this is just another example. We don't have time to go through fully, but some students liked that in the past. Okay, we're going to analyze a couple graphs we don't want to write, but let's look at a couple of questions. Use the graph of f prime to analyze the original function of f. Okay, so what do we know? Well, let's start off with this. Critical points. Where does the derivative equal 0 or not exist? Notice, we have potential critical points. Critical points are when the original derivative is equal to 0, so at x equals 0. At x equals 1, the derivative does not exist. That's the first time we saw this happen. There is an empty circle there, which means it doesn't exist. And then at 2, the derivative is equal to 0 as well. Now, we should check for a sign change. Notice, this derivative is positive. If I did my sign chart here, at 0, 1, and 2, I have positive f primes because I'm above the x-axis. I have positive spots here, and then I have positive here, and then negative. So, what conclusions can I make? Well, because this should be filled in, but there's a flat spot at 0. There's probably a discontinuity. We're not sure, but if the second derivative does not exist here, there might be some type of discontinuity. We would have to know more information, but there might even be a cusp or a vertical tangent or something else. So we just don't really know what's happening at 1. But at 2, I go from being above the x-axis to being below, or if you think of the sign chart, I have positive slopes to negative slopes. There's a maximum here. We have a maximum at x equals 2. Okay. Now, what about concave up? Well, let's look at the slopes. If I want to find positive increasing derivatives. So here I've got negative slopes, but from 0 to 1, my slopes are positive. Right? These slopes are increasing from 0 to 1, where if I was to graph the second derivative, I know that all of these would make f prime positive. It's increasing slopes, which means that's concave up. So what about concave down? Well, concave down is where the slopes of the derivative are negative. So see how my slope, the tangent lines here, are negative? And then this is a linear function. We have to be careful here. But they are also decreasing. They're decreasing at a consistent rate, but it's still concave down. So we'd be concave down from negative infinity to 0 and from 1 to infinity. So all of that, and actually, we know there's a point of inflection. Point of inflection changes from where I go from concave up to concave down. Well, here, I went concave down, concave up. So this point right here is a point of inflection, and there's a sign change. We go from negative to positive. And then here, even though it's undefined, we have a second derivative that doesn't exist, but we still change signs from positive to negative. So all of that information can be determined about the original function there. And then that ties in. What do we know about f double prime? That's the concavity. So you could say, because f prime is concave up, we know the second derivative is positive on the interval from 0 to 1, concave up. And because f of x is concave down on these two intervals, that means the second derivative is negative. So a lot can be interpreted from a graph. Don't write this one either. I just want to show you how quick a problem like this could be. So if I give you a table is the same thing as a graph, right? They're going to give me some information. Let's make a sign chart for f prime. All right, so where is f prime equal to 0? Right here? Or where does it not exist? At x equals 0, the derivative 0. At x equals 3, it doesn't exist. So those are potential critical points, right? And then what do I know about the slope between those points? Well, the interval starts at -3, so I wouldn't check points past that. And then this is for anything greater than 3. But notice our graph would stop at -3. The points between 3 and 0 are positive. The points greater than 3 are negative. So right here, what do you know? If the derivative goes from positive to positive, there's a flat spot there. There's no sign change. But if I go from positive slopes to negative slopes, there's a minimum right there. If the point exists. Now we got to look at that. It doesn't exist, but that tells us a little bit more. And then what about the sign chart for the second derivative? And now I'm looking for, where does the second derivative equal 0? That's at 0. Or where does the second derivative not exist? And those are at 3 as well. And then what about the concavity? Right? Between these 2 points, between -3 and 0, I've got negative slopes, which is concave down. Between 0 and 3, I have slopes that are positive, so this is concave up. And then between anything past 3 is positive as well, so concave up. Okay. Now you could also, I should have mentioned this, f prime is positive, so therefore the original function is increasing, increase, decreasing. So all those conclusions that we've learned can still be true in a table. My recommendation is, if I give you a table, turn it into a sign chart, and you'll be able to make a lot more conclusions faster. Okay, here's what we got for homework tonight. We don't have anything new. Your homework tonight is to finish 5.3 day 1 from last Thursday, Friday, and the AP quiz 5.1 from Wednesday. Okay? This Wednesday, I thought I put that in here. you are going to be asked to watch a video. I did not create it yet, but on Wednesday, you just have to watch a video, and that's the work for Wednesday. Okay? I may put it in Edpuzzle. I'm not sure if I know how to do that perfectly, so I'll tell you in the instructions on Wednesday if I was able to upload it to Edpuzzle or not. So homework today is basically get caught up on all the other stuff. All right, that's all I got. I'll be available from 1 to 2 today. If you have any questions,